New topic, part B, asymptotic notations. B.2, Introduction to Asymptotic Notations. We learned the growth functions in part A. After that, because in order to characterize growth functions, we want to have some concise notations. So starting here from this video, so we will learn this new concept, asymptotic notations. All right. So let's recall when we compare two growth functions. How do we do it? We take limit of the ratio of two growth functions when n goes to infinity. In that procedure. So here, the first question, when we do that, using that limit, typically, how many cases do we have? Right? Yep. So look at this ratio when n goes to infinity. We consider all the possibilities. How many cases do we have? So look at these cases. The first case, 0. The limit is 0. The second case, non-zero constant c. So this c cannot be 0. Okay, so we separate. So non-zero constant c, but another thing, when we compare two growth functions, we assume the growth function positive. It is pretty natural because when we talk about growth functions, we use the counting numbers of some operations. Those counting numbers, definitely, they are positive. Okay? Yeah. So that's the second case. The third case, infinity. Other than these three cases, the last case, the limit does not exist. Because you cannot guarantee the limit always exists. The limit may not exist, right? Yeah. So we have this other case. All right. So next, so let's do some discussions on these four cases. What information do we get for these four cases? The first case, because the numerator, when n goes to infinity, the limit over the denominator approaches to 0. So definitely the denominator increases faster, much faster than the numerator, right? So based on that intuition, we can say the order of growth of f of n is less than order of growth of g of n. There is some order. Okay? Yeah. So here, actually, this order, although we use this term, but it is not easy to use a number to represent this order. Yeah. Because the growth function could be like this. Yeah. Remember, in the example we used the last time, the growth function could be this one. How can you use an order number to represent it, right? How can you use an appropriate order number to represent it, right? Yeah. So although we have this order term, but it's just some comparison type. We can compare. One growth function has larger, higher order than the other, but usually we do not say order number. Yeah, because it's hard. Sometimes we couldn't choose an appropriate order number. Yeah. All right. That's case number 2. Yeah. Non-zero positive constant C. In that situation, we can say these two functions have the same order, because the difference just the constant multiple. And that constant in our algorithm context, we do not change the order. Non-zero, yeah. So let us understand this way. A non-zero positive constant, if you multiply a function or not, it does not change the order of the growth of that function. Okay? Yeah. So that's the case 2. Case 3, infinity, right? Infinity. Yeah. So the numerator increases much, much faster than the denominator. Infinity, so we say the numerator has larger order of growth than that of the denominator. Yeah. That's the first 2 cases. But the last case, case number 4, very hard to say anything about order of growth, because we don't have enough information. Yeah. Hard to say. Any of the 3 cases is possible. Could be order of the numerator less than order of the denominator. Could be, let me see. Now here we should be careful. Yeah, here we should be careful. Right. Yeah. Although at this point not enough information. Yeah. But yes, I have to correct a little bit. Yeah, because if the order is less than, then the limit has to be 0. All right. So let me try to clarify. Yeah, because this part is very easy to get confused. Yeah. Sometimes I also get confused by myself. Yeah. All right. Let me clarify another time. If, let's say conversely, if the order of growth of f of n less than order of growth of g of n, then we must have that limit equals 0. Okay? All right. Now, if the order of growth the same, do we have to have this? Not necessary. Be careful. Number 2, if someone tells you we have this, we have the same order, it does not mean you have the ratio of those 2 functions equals non-zero constant, positive constant. Not necessary. That could be case 4. Okay? Yeah. So 2 possibilities. Same order, 1 possibility, limit equals non-zero constant positive c. Another case 4, the limit does not exist, but we can still get same order. Yeah. So we will discuss next slide more about this one. Yeah. Case 3, order of growth of the numerator greater than that, we must have infinity case. We must have the infinity case. Only for the case 2, same order of growth, there are 2 possibilities. Yes, now it's better, right? Now it's better. Yeah. One is the ratio has the limit non-zero constant c, positive, for the growth function, because we look at the positive functions, positive c. The second possibility, the limit does not exist, but still we have another way to get it, another way. So we will talk about that next slide. Yeah. All right. So now we want to look at a different way to give us more information for case 4. Yeah. So what's the way? So the limit way has some limitation. Yeah. All right. Yeah. So what's the limitation? Yeah. Here, let me show you. Yeah, because you may wonder why the limit does not exist. Why it could happen, right? Yeah. Some of you may ask this question. Why the limit of the ratio may not exist sometime, right? Sometimes. Here, let me give you a simple example. Simple example. Consider the ratio of these two functions. N squared, numerator, how about this function? Okay, so no problem, right? Yeah. Denominator, this function. When you take the ratio, we can cancel out n squared, right? Numerator, denominator, we can cancel out n squared. After that, look at the ratio of these two numbers. Two numbers. Can you see the limit does not exist? Right? So let's take a look. When n is even number, okay? Even, odd. When n is even number, we get the ratio 4/1, right? When n is odd number, what's that? Odd number, 2/what? 2/3, right? Alternatively, so you see two numbers, 4/2, 4/2. This pattern, alternatively, to the infinity, this trend to the infinity. Is there a limit? No limit, right? Up and down. So it will not converge to a fixed number. When we say there is a limit, those values should converge to a fixed number. That's why it does not converge to any number, right? Yeah. So that is the example. Okay. Yes. Because of that, so we need a new method for case 4. The new method should not rely on the limit. We don't use limit. Yeah, to avoid that non-existence situation. Yeah. All right. So our objective, even if the limit of this ratio does not exist, we can still compare two growth functions. How? How to do it? Yes. Yeah. How to do it? Okay. Yeah. Yeah. Here, let me leave the formula there. Okay. Yeah. So you can see this example. Yeah. All right. So let's go to the next slide. Oh, yeah, sorry. I have something. Yeah, I have to erase. Yeah. Let me erase this part. Yeah. And leave the bottom part. Yeah. All right. Then here, let's look at the notations. Concise, compact notations. Yeah. For this case, we use little o. F has smaller growth order, so we use the little o. And also the limit equals 0. This case, we use big theta. Big theta, when you see that, they have the same growth order. Yeah. one of the two cases, limit equals non-zero constant c, non-zero positive constant c, but there is another case we will learn next slide, big theta. Yeah. This one, small little omega, okay? Yeah, this case, limit is infinity. So do not get confused. Little o, limit equals 0. Little omega, the limit equals infinity. Big theta, same order. The limit equals non-zero positive constant. That's one of the two cases. There is another case we will discuss in the next slide. All right, this slide. Okay, so let's discuss this situation. The limit does not exist, okay, this situation. All right, here we use upper bounds and lower bounds. Upper bounds and lower bounds. When the limit does not exist, we can use upper bounds, lower bounds to avoid taking the limit. But another point of view, even if the limit exists, we can still use upper bounds and lower bounds. It's still okay. Yeah. So we can use two ways, the limit way, upper bound, lower bound way. Yeah. All right, so let's look at the detail. How? All right. So here, usually, when we consider the g function, we like to use relatively simple functions. Because in that way, we can get idea of some more complex function better. We use relatively simple functions to describe some relatively complicated functions. Yeah, so that's the reason we use this way. Yeah. All right. Then, yeah, so the f of n could be a complex or complicated. Yeah, because complex may have some different meaning, right? Complex, real complex. Yeah. Complex could have a different meaning. Yeah. So here we mean complicated. Okay. Yeah. Complicated, that meaning. Yeah. Not the real complex, that meaning. Okay. Yeah. All right. Use some constant multiples of g of n to approximate f of n. Yeah. So the idea is this. Yeah. Upper bound, lower bound. What kind of upper bound? What kind of lower bound? Constant multiple. Some constant multiple as the upper bound, lower bound for our goal function. F of n, that's our function to be studied, that function. Yeah. Yeah. Specifically, we use two positive constants, C1, C2. C1, C2 multiple of g function to approximate f function. So that is the idea for this asymptotic notation. Yeah. So it's something like this. We try to find C1, C2 positive constant such that this inequality holds. If we have that, then we can say these two functions, f of n, g of n, they have the same growth of order of growth, same order of growth. Big theta, or we say f of n belongs to big theta of g of n, right? Yeah. Or is contained in big theta of g of n. Yeah. All right. Yes, that's our second method, upper bound, lower bound method. Yeah. Also pretty simple. Yeah. And this method also works for the limit case. But when you have if the limit exists, usually it is a good idea to take the limit. It is a good idea to take the limit. Yes. Because limit is a powerful tool we can use from calculus. So we don't want to throw away. It is a powerful tool. So we still want to have it, the limit tool. Yeah. All right, next, we try to understand various asymptotic notations. Its definition. The definition. Oh, all right. Big O notation. Yeah. So we learned 3 asymptotic notation. At this point, little o, big theta, little omega. Okay, 1, 2, 3. This one, big O, number 4. The 4th asymptotic notation. Yeah. So look at the definition. For a given function g of n, the notation big O of g of n represents the set of functions for those f of n that satisfy the following condition. Okay, upper bound condition. There exists some positive constant c and some non-negative integer n0 such that f of n less than c times g of n for all n greater or equal to n0. That's the definition. That's the definition. Okay? Yeah. But here, we need to understand the special integer n0. Non-negative integer n0. Why we choose this one? And there exists some positive constant c and some non-negative integer. So you can find appropriate two constants. Okay? One is that c, another is n0. Yeah. All right. And what kind of property this n0 has? It has this property. Okay? Before you choose it, you have the freedom to choose. Okay? And not necessarily 0, 1, 2, 3. You can choose it as 100, 1,000, even 1 million is okay. So before you select it, you have freedom to choose that n0. But after you select it, you must fix it. You only have one chance to choose. After you select it, don't change. Okay? When n changes, you are not allowed to change, right? So you should select appropriate one. After you select it, then fix it. Fix it, it means it does not rely on variable n value. When n changes, we use the same n0 constant. So that's the property of this n0 constant. Yeah. And we only want to make this inequality true for all n greater than or equal to n0. When n less than n0, we don't care. It's true or not, it doesn't matter. We don't worry about it. It doesn't matter. Why is that? Okay, let me give you a quick explanation. Why is that? The reason is, remember we learned before the overhead part, right? When n is small, right? When n less than n0, we treat n is relatively small. When n, the problem size is relatively small, the overhead part may be too big. So we don't want to consider, how fast function grows if the overhead part is too big. So we want to ignore it. Ignore the part affected by the overhead. We want to push that N0 far enough such that after we pass the N0 line, we never need to worry about the overhead. So we have this inequality hold all the time after we pass that N0 line. So that's the meaning. Yeah. So the background, that overhead background, is useful here. Yeah. All right, so let me finish this video here. In my next video, I want to give you graphical explanation of the asymptotic notations. Yeah. So we want to have a visual understanding on the asymptotic notations. All right, so let's stop here. Yeah.